In this video, we'll be going over the pumping lemma for context-free languages. I'll begin by introducing the lemma itself, then I'll move on to proving that this lemma does work and how it works. And finally, using example languages, I will demonstrate how this lemma can be applied. Naturally, the pumping lemma for context-free languages is a little bit more complex than the pumping lemma for regular languages. If you recall, the pumping lemma for regular languages, which we do have a video on if you would like to refer to it, decomposes a word of your choice into 3 subparts, whereas the pumping lemma for context-free languages will be splitting it into 5 subparts. The pumping lemma for regular languages pumped up the single middle subword, whereas the pumping lemma for context-free languages will have 2 sufficiently long substrings, which we will be able to pump in equal amounts to give another word that should also be in the given language. Like the pumping lemma for regular languages, the lemma cannot be used to prove that a language is context-free, but it can be used to prove that a language isn't context-free. So let's begin by looking at this theorem as a whole. The pumping lemma says that for a given language L that we know is context-free, there will exist a constant k such that any word said that we know is in this language and is greater than this k in length. For such a word, there will exist a decomposition into 5 subparts, u, v, w, x, and y. There are 2 conditions we need to follow when decomposing this word z. The first is that the middle portion of the word, v, w, and x, have to be less than k in length. The second condition is that the sections that will be pumped, v and x, cannot both be the empty word. Either v or x or both have to be at least greater than 1 in length. The reason why both v and x can't be the empty word is because this is one of the useful properties of Chomsky's normal form. Starting from the start symbol, each non-terminal has to produce a terminal followed by another non-terminal, or the final non-terminal ends the path with a terminal. If these 2 conditions are met, then for any value I that is greater than or equal to 0, pumping v and x by I in equal amounts will construct a pumped word that is also in this language L. Now that we know what the pumping lemma entails, let's move on to proving why and how this pumping lemma works. The proof starts with the Chomsky normal form grammar for the language L. This excludes the empty word, but that doesn't matter because the empty word can never meet the condition of the word being at least k long. Next, let the constant n represent the number of different non-terminals the grammar has. We can say the pumping lemma's constant k is 2 to the power n. Let the word s of length greater than or equal to k be a word that is in the language L. Although I have typed out n over there, that was a typo. It was meant to be k, so the word has to be of length greater than or equal to 2 to the power n. We claim that a parse tree that yields the word s must have a path of length n plus 2 or more from the root to the leaf. We are now going to prove this claim. A basic parse tree for the Chomsky normal form grammars starts from the root, which is the start symbol, and produces a terminal and a non-terminal at every level for each non-terminal. So, at the very last level are the leaves, which are composed of only terminals. And this gives you the yield of the word. With the exception of the very last level, we see that the growth of a parse tree is a binary tree, meaning each node produces 2 more nodes. The very last node, labeled as the non-terminal, produces a single terminal. The claim here is that if all the paths in the parse tree of a Chomsky normal form grammar are of length less than or equal to n plus 1, where n is the number of nodes on that path, excluding the very first note as the root, then the longest yield will be 2 to the power n minus 1. If we consider this tree, all the paths on this tree are of the same length. At the nth level, there can be at most 2 to the power n minus 1 nodes. The largest number of leaves occur if all the paths of the tree have exactly n variables, meaning if all the paths on the tree have exactly n non-terminals. If we look at this tree, on the first level, which only has the single root, The yield of the first level is 2 to the power 1 minus 1, which is 2 to the power 0, which is 1. On the second level, the yield of the tree is 2 to the power 2 minus 1, which is 2 to the power 1, and it is indeed 2. On the very last level, which is the third level on this tree, the yield is 2 to the power n minus 1, which is 2 to the power 3 minus 1, which is indeed 4. So from this we can conclude that there are 2 to the n minus 1 nodes that are labeled as non-terminals and have a single child with a terminal label. Thus, there are at most 2 to the n minus 1 leaves. So we can conclude that the yield of the parse tree of height n is 2 to the n minus 1. 2 to the n minus 1 is the same as k over 2 because we chose k to be of length 2 to the n. Since the word s is of length k, the word s cannot be the yield of any tree that has paths that are limited to the length of n plus 1 or less. Therefore, somewhere in the parse tree of the word s, there must be a path of length at least n plus 2. We've just proved that the parse tree of the word s will have a path of length at least n plus 2 or longer. Only the last node on any path can be labeled as a terminal, so there are at least n plus 1 non-terminals. Consider the longest path, so surely there are at least n plus 1 non-terminals along the longest path. Remember, n is the number of different non-terminals, so along the last n plus 1 non-terminals on that path, we can find 2 nodes with the same non-terminal label. We can say that this non-terminal is capital N, meaning at least one non-terminal appears twice in the parse tree. So this is what the parse tree will look like. The word S starts from the top of the triangle at the root and first produces the substrings U and Y. At the first occurrence of the non-terminal N, we produce V and X. At the second occurrence of the non-terminal N, we end the production of the whole string S with the substring W. So W is rooted at the lower n, and the yellow tree, which represents V and X, with the light blue tree for W within it, is rooted at the upper n. The reason why both V and X can't be empty is because we eliminated unit productions, as all non-terminals have to produce at least 2 variables, unless it is the very last node, in which case it can produce 1 variable. So with that, we can conclude that V and X, or both, have to have length at least 1. S, in this case, is the word that we get when S is of a sufficient length of k. When S is of a sufficient length of k, the parse tree for the word S has a sufficiently high derivation tree for there to be one reoccurrence of the same non-terminal n along the path of this parse tree. We can get rid of one of the n's along the path, and this removes the V and X section. So if you notice here, the V and X can be directly substituted for W. This is because the condition for a parse tree is that every interior node has to be the head of the production of another subtree. In case that wasn't very understandable, I can explain this in another way. So, in other words, if we followed the general idea of a parse tree, starting from the root, the non-terminal we end with has to be the start of the next subtree. Where n appears, we can either insert V and X or W because both trees have the variable n at the root. It's almost like a puzzle piece where you have to fit in the right piece. The right piece could either be V and X or W. So after the initial U and Y, if we choose not to insert any of the V and X sections and directly insert a W, we get U, W, and Y. The word U, W, Y is when V and X are pumped to I equals 0. Similarly, from our original word S u, v, w, x, y. Instead of removing the second occurrence of n and thereby removing v and x, we can add another reoccurrence of n and add another pair of v and x to generate the word u, v square, w, x square, y. Similarly, we can continue adding v's and x's before ending the production with a w, so we should be able to generate any word in the form of u, v to the I, w, x to the I, y, where I can be any integer greater than or equal to 0. Now that we've proved that the pumping lemma works and have gone over the lemma of how it works, we're going to show how to apply it using example questions. But before we get into any specific questions, it is useful to know that in general, languages of the form a to the I, b, c to the I are generally context-free. This is because it's possible to calculate one pair of counts. So we can count the number of one alphabet in relation to another. However, languages in the form of a to the I, b, a to the I, b, a to the I, where you're required to count two pairs, the first occurrence of a to the I with the second occurrence of a to the I, and the second occurrence of a to the I with the third occurrence of a to the I, or alternatively, when you need to count three variables in a group, such languages are not context-free. This is because although context-free languages can calculate one pair of counts, it can't match two pairs or three counts as a group. Now, if the first language, a to the I, b, c to the I, is context-free, if this language were instead to be the language of a to the I, b to the I, c to the I, where instead of counting a pair, we're counting three variables together, this language would not be context-free. And this is the language we're going to use for our first example. We'll be applying the pumping lemma to the language a to the I, b to the I, c to the I, where I is any integer greater than or equal to 0, and prove that this language is not context-free. Just like the pumping lemma for regular languages, we first have to assume that L is a context-free language. Let k be the constant from the pumping lemma, which represents the length a word from this language can be. And this word, which we will call z, is a to the k, b to the k, c to the k. The only condition for the length of the word is that the word has to be greater than length k. And this word is 3 times the length of k, so therefore it is indeed greater than k in length. Now that we have a suitable word z, which we know is in this language, for such a word, we should be able to decompose this word into 5 subparts, u, v, w, x, and y, with the constraints that the middle section, v, w, x, has to be less than or equal to k in length, and not both of v and x can be empty, so the length of v and x combined has to be at least greater than 1. And if these two conditions are met, then for all I that is greater than or equal to 0, pumping v and x proportionately by I will give a word of the form u, v to the I, w, x to the I, y, which should also be a word in the language. When decomposing this word, other than these two conditions, what we need to keep in mind is that context-free grammars can be ambiguous in their productions. Unlike regular grammars, which are either left linear or right linear, context-free grammars can be built in any order. Therefore, when we're picking the v, w, and x section from the word a to the k, b to the k, c to the k, v, w, and x can be within only a's. It can also contain some a's and some b's, or only b's, or some b's and some c's, or all c's. We need to consider every possible decomposition of the word z individually. If v contained some a's and some b's, or some b's and some c's, then pumping the v section by v square would give some number of a's followed by a number of b's followed by that number of a's and b's repeated again before ending the production with c's. Or we would have k's followed by some b's and some c's followed by another block of b's and c's before ending with a block of c's. In both cases, the segregation of the 3 blocks of letters are broken. Therefore, to preserve the separation of the three blocks of letters, V has to be composed of a block of either only A's, only B's, or only C's. However, pumping this decomposition constructs a pumped word of the form A to the k plus I, B to the k plus j, C to the k plus L. This pumped word would break the proportion of each block. At least one of I, j, or L has to be a value that is not 0. This means at least one of the blocks of k letters will now be greater than k in length than the other two blocks. And therefore, the pumped word A to the k plus I, B to the k plus j, C to the k plus L is not in the language L. This is a contradiction to what the pumping lemma should result in. If the language L was a context-free language, then decomposing and pumping a word in the language should have resulted in a word that is also in the language. But no matter how we decompose the word Z, the pumped word is not in the language. So by this contradiction, we can conclude that our initial assumption that this language is context-free is wrong. This language is in fact not context-free. So, using the pumping lemma, we've just proved that this language is not context-free. I hope this explanation was useful, because using this example, I will now be leaving you with 2 questions for you to solve, and the solutions will be given in another video, but please do have an attempt at it yourself before checking the video with the solutions. I hope this explanation was thorough enough to understand, but concise enough to not be loading you with unnecessary theory. Thank you for watching. If you found this helpful, please support our page, like, share, and subscribe. And if you have any further questions, suggestions, requests, constructive criticism, or even corrections, please do leave a comment. We'll try to answer as soon as.